Hi, I'm Daniel Sellers, and this is my poster on equilibrium solutions for 2D non-axisymmetric disks. So what we're looking at in this study are disks of gas and stellar matter in space which have enough mass that we have to account for the gravitational effect of that mass on all the other particles within the system. And these disks are also thin enough in one direction compared to the other two that we can approximate them as being two-dimensional. And since this study, as you'll see, is computational in nature, that's an advantage because 2D systems are much easier to compute than 3D systems. So these disks are governed by a set of equations, two partial differential equations, and what's known as a scalar momentum equation, which you'll see written under equilibrium solutions there on our poster. And the PDEs in question are the Poisson equation, denoted capital Phi in this study, for gravitational potential within the disk, and psi, which denotes the stream function equation, which can be thought of as sort of a velocity potential for circulation within the disk. And for a given density distribution, these PDEs can be difficult or even impossible to solve. But we need them because what we're ultimately seeking in this study is equilibrium solutions, that is, density distributions and solutions to these PDEs, which satisfy the scalar momentum equation and which constitute solutions which are not changing in time. And so what we're going to do is we're actually going to iterate and allow this C sub I value that you see there to change over iterations until the change between steps becomes very small. But to do that, we're going to need these PDEs solved at each step. So to solve them, we put them through a process called discretization, which is where we rewrite the PDEs in such a way that they no longer operate over a continuous space, but over a discrete polar grid. That is, they're only defined at certain distinct grid points. And then we use a process known as a Guass-Seidel algorithm to supply an initial guess and allow the algorithm to iterate until, again, the change at each grid point becomes small, and we call that convergence. And we have, under methods, a plot of one grid point converging to its final value. And so we can verify these PDE solutions, at least partially, by asking this question. If we have a simple enough situation, say a very simple disk, like one that is axisymmetric, that means the same in all directions and of uniform density, we can actually solve these PDEs exactly and then compare our numerical solutions. And so we've done exactly that under analytical solutions in the lower left. You'll see psi and phi both solved exactly, and the numerical solutions from the center of the disk to the edge along one x-axis. So the ultimate idea is, again, to find these overall equilibrium solutions. So we take psi and phi and put them into this scalar momentum equation, and we use the results of that equation to generate a new density distribution, which then repeats the whole process over again, finding psi and phi and allowing a new value of c sub I until we have convergence. And so these plots down in our lower box equilibrium solutions show a couple of converged density distributions. Now, unfortunately, most of the parameter space we're exploring seems to not converge to physical solutions, or perhaps are outside the range of functionality of our algorithms, and so we have relatively few converged solutions so far. And the parameters for these solutions were mostly taken from Andelieb's 1993 dissertation on a very similar topic of 2D non-axisymmetric disks. And so under conclusions and future research, we have just a couple images, a velocity field that's generated from our solutions on top, and a velocity field provided by Andelieb below that. And if you look closely at these, you'll see that there's not a lot of agreement between them. They have different shapes and different flow patterns within the disk. So not a lot of agreement with our source material yet. We are still looking to see if we can agree with some of those models more closely, but also just refining this whole procedure, because we eventually want to take this method of iterative solutions to these 2D disks and apply them to more complicated systems, systems perhaps relating to binary star systems or other more complicated disks than just these sort of simple ones we're looking at now. So I would like to thank Professor James Imamura for his guidance and expertise and for the awesome opportunity to work on this project. And thanks also to my classmates here at the University of Oregon and my very supportive wife, Miranda. Thank you.